All right. How fun to be able to present to you today on such an interesting topic, quantum computing and the security implications of quantum computing. Before we start out, I just want to ask everybody who here kind of, knows quite a lot about quantum computing? All right, just a few people. Yeah, I think that's the usual story that I see. It's a very new thing, and it's an up-and-coming thing, and it sort of promises to be a disruptive technology in the future, if and when it's realized sometime in the future. But meanwhile, there's been so much progress on it, I think it's really made a lot of headlines and has been something that people have sort of seen and thought about and been interested in for a while. And I think we're all due to sort of learn more about it, don't you think? The first thing I wanted to do is to introduce you to a quantum computer. So here you go in the picture. What you see here is the well-publicized IBM Q System 1. And it actually, to tell you the truth, I saw this, a demo of this not long ago in the Computer History Museum itself when there was a related conference on this subject matter. And it was announced in January of 2019 officially. It is a 20-qubit commercial quantum computer. It was developed by IBM Research. And it's a little hard to see there, but there's sort of this big glass chamber around the whole thing. And then the quantum computer, the IBM Q System 1, is sort of this barrel thing that you see in white down in the middle. And if you're wondering what it looks on the inside, well, I couldn't find the exact picture, but IBM has similar models, and shown here is sort of another part of the IBM Q series that looks pretty similar to probably what's inside of the IBM Q System 1. As you can see, it's a very complicated machine, don't you think? And it really looks a lot different than things you've seen before. So it's a pretty fascinating story. All right, so yeah, what is in a quantum computer exactly? And the IBM Q System 1 has a nice set of beautiful materials online that tell you a little bit about some of the internals, and I grabbed one of the pictures of it here so I could show it to you during this talk to kind of show you around a little bit. Gosh, the first thing to say about this thing is, interestingly, it has a very sophisticated cryogenic system that will cool the whole thing. Check this out. So, the processor, which I'm going to point out in just a second, is kind of toward the bottom. And the cryogenic system is the refrigeration system, which is known as a dilution refrigerator. It has more than 2,000 components. Go figure. It uses a mix of helium isotopes to create temperatures that are near 0 Kelvin, near zero. So as you see on the slide, that would be about minus 452 Fahrenheit, going down to minus 459.373 Fahrenheit. So the technical challenge of cooling a quantum computer to a very, very low temperature like that is one of the big challenges and helps to explain what all the apparatus is inside of a quantum computer. By the way, why are they trying to cool it? Do you know? Yeah, so I'll talk about this a little more, but the quantum computers are using a quantum physical phenomenon in a controlled way, right? And the problem is that quantum physical phenomenon is affected by the surrounding environment in a big way. And so what you're trying to do is to sort of stabilize this element in a way that allows you to have control and persistence in it, so that the outside elements, which are very noisy, don't cause disruptions. And so part of that, for most of the qubit technologies, has to do with very extreme cryogenic systems that are cooling things down to this extent. Okay, so a couple of labels about this. So The input microwave lines, let's see, they use attenuation at applied stages in the refrigeration in order to protect the qubits from the thermal noise during the process of sending control and readout signals to the processor. The mixing chamber is right here. It's sort of the lowest part of the refrigeration unit, and it cools things down to a temperature of approximately 15 millikelvin. By the way, 15 millikelvins is actually colder than outer space. So, wow. And then the quantum processor itself is in this part. It's in the cryoperm shield. The quantum processor sits inside of the shield that protects it from electromagnetic radiation in order to preserve the quality of that quantum physical phenomenon I was telling you about. And then this part right there is the quantum amplifier. It will amplify, it also is inside of a magnetic shield, and the idea is to magnify, to amplify the processor readout signals while minimizing the amount of noise that it introduces. So yeah, this is really cool stuff, and I encourage you to go to IBM web pages that talk a little bit about the IBM Q System 1 and some of the aspects of this kind of technology. It's very impressive stuff. Oops. All right, so at the heart of quantum computing is the notion of a qubit. And the qubit, I have to tell you, it's a really interesting technology research domain. There have been all kinds of approaches to how to create the kind of physical phenomenon that can be used as the basis for a quantum computer, that is the qubit technology. And listed on this slide are some of the approaches, and I won't go through the whole slide. It's kind of each one is sort of its own story. But I just want to point out a few of the technologies on the left side, on the column on the left. And one of the ones that's most common is the superconductors. And the superconductors are essentially using superconducting electronic circuits that are cooled to a very low temperature, as I've been saying. They use Josephine junctions, which is sort of this weak connection between the superconducting wires, and it causes this quantum tunneling effect through the junction. And that's how they're able to get a controlled quantum physical phenomenon that they can use. Linear optics is another one. Here they're using photons, and the photons are sort of directly translated to quantum information bits, and they use equipment like beam splitters and phase shifters and mirrors to sort of manipulate photons in particular ways. Another one is quantum dots. In quantum dots, you have a nanoscale semiconductor material that is somehow able to trap and confine an electron or some kind of atomic spin that's going on inside of it. And neutral atoms. In neutral atoms, you take electrically neutral atoms and you trap them by laser light in certain ways in order to create 3D structures like a cube in various ways, and then to sort of perturb them in particular in sort of controlled ways. And one last thing I'll mention is topological quantum computing. Now this is really an interesting one. It's still theoretical, and it's about using two-dimensional quasi-particles which pass around each other and form what they refer to as braids. The braids are sort of in space and time, and they sort of bind together in a way that is supposed to be a very stable thing as opposed to trapped particles. And so the Majorana particles are sort of a key candidate to realizing that kind of topological quantum computer. So the message that I really want to leave you with is that, yeah, it's really not clear exactly what to use in a quantum computer, and it's fascinating, all of the different branches of physics research that are going on, looking at different types of qubits and which one is most stable, which one is most controllable, which one is most easy to work with in order to make a scaled quantum computer. So let's stand back for a second and overall, what is a quantum computer? So you could describe quantum computing as being a model of information and computation that builds on the quantum mechanical view of atomic scale systems. So some of the properties of a quantum physical system are that the description of nature is probabilistic. I'll show you that in a second. That it's not possible to know the values of all the properties of the system at the same time, and those that are not known are described by probability fields. And that measuring devices are classical devices and measure only classical properties. So in the world of quantum computing, they refer to conventional computers as quote unquote classical computers, right? And classical computers, as we know, are based on bits. The bit is an electronic device that holds a single value, holds a single state. It's either a 0 or it's a 1, right? If you have several of these things, then you can create a register. That register can have one of 8 values, as shown here. You know, but in the world of quantum, you have qubits. And a qubit, which is making use of this quantum physical phenomenon, actually holds probability fields of more than one value at the same time, right? What you see here is a block sphere. And it's a diagram kind of portraying this idea. The basis vectors at the bottom and the top are the possible values. And the position on the sphere is telling you what the probability is of the basis on the top versus the basis on the bottom, okay? And so the amazing thing about this is that it can simultaneously model, if you had 3 qubits, you could simultaneously model all 8 of those states at the same time. Okay, and so in general, a register of n qubits can represent 2 to the n probability distributions all at the same time. That's very powerful stuff as n gets large, right? Very powerful stuff. All right, so I thought I'd play kind of this fun matching game as a way of telling you 5 key concepts in quantum computing that you should know, okay? And so the first one is superposition. All right, so what's the definition of superposition? Do you see it? Which one do you think? That's right, the third one. Okay, so the idea of superposition is that quantum states can be added together, resulting in another valid state, and that every quantum state is the sum of distinct states. Okay, so once again, the contrast between classical and quantum, right? In classical, if you were to overwrite the state of one of the bits, it will change the state, so now it has a new state, right? But in quantum, the notion of superposition is that you can take states and kind of add them to the state that's being held by the quantum physical phenomenon. So you have this notion of superposition, right? Adding more states to what's being held by the quantum computer. Entanglement, what do you think? Okay, I think the first one, right? Entanglement, particles share the same space and interact such that the state of each cannot be described independently of each other. Okay, so in some ways, entanglement is really at the heart of what quantum computing is really trying to do. Highly entangled quantum states hold a huge amount of information. It's impossible for classical computers to describe all of the correlations that are held in the entanglement. And it makes it possible to model complexities that are beyond the reach of classical computing. I have to pause for a second and tell you, you know, my favorite little anecdote about how to think about entanglement comes from John Preskill, the Caltech professor, and I'll mention a quote from him toward the end of the talk. And he says it like this. Okay, so just a way to, kind of an analogy to wrap your brain around, right? Suppose that you had a book, and that book represented classical computers, right? The way that book is going to hold information is that the information will be listed on the pages explicitly, right? So you have some page, it has explicit information, the next page has some explicit information, and the sum total of all of the information in this book is the sum total of all the pages, okay? No surprise. But if you had a quantum book, right, a quantum computing book, you would have a little bit of gibberish on the pages. And most of the information that is held through entanglement is being held in a way that it's in the correlation between all of the pages and isn't visible on the pages themselves. And that's kind of an analogy for what's going on in the qubits that are entangled with one another within the context of quantum computing. It's holding an exponential amount of information that isn't explicitly shown in the state itself because you have probability distributions that are holding the entangled state for all of it. Okay? The next one, measurement. Oops, I didn't give you a chance to guess. Okay. Sorry about that. Yeah, trigger happy. So measurement, an important concept in quantum computing is remember that quantum computers aren't like a massively parallel system that's doing everything all at the same time. It's more like a massive complexity of state that you can operate on in various ways until it's time to get an answer. And when you get an answer, you use classical measurement, and that grabs a classical value. So it's sort of like the quantum physical phenomenon will collapse based on the probabilities to a single value. You measure that value, and so you'll see that quantum algorithms are kind of like that. They will set up a superposition, they will manipulate that superposition until finally the adjustments in the probability ranges are such that a classical measurement is made, and voila, that's your answer, and that's how it's working. Okay, decoherence? Yes, the bottom one, noise. We kind of talked about this. Decoherence is the noise from the environment causes the quantum behavior of a qubit to collapse. And the whole story of quantum computers is, can somebody invent a qubit that has long coherence times, is high in quality, has low errors, and can be in a coherent state for a long time? And then finally, supremacy. So supremacy is the universal quantum computer. Okay, so supremacy is something that I think everyone here should watch in the tech news, right? They'll be talking about supremacy, I think probably in the near future, hopefully. The notion of supremacy is that the quantum computer has done some kind of computational task that is beyond the reach of classical computing given a reasonable amount of time, okay? Do you think we already have quantum supremacy? Has quantum supremacy already been shown? What do you think? Yes? No? Okay, it's a little bit of a tricky subject, so sometimes the answer is not clearly yes or no, but I think overall the answer is no. Hasn't been shown, okay? So it's a very exciting matter to watch the tech press and quantum computing to see who and when will be able to demonstrate strong evidence of quantum supremacy. We live in exciting times, okay? Okay, state-of-the-art quantum computers. What are the state-of-the-art quantum computers? Well, here you go. Two that are particularly at the forefront are IonQ 79 qubit trapped ion processor. It was announced in December 2018. And Google's 72 qubit bristlecone, which was announced in March of 2018. Now, what makes these quantum computers state-of-the-art it's actually a long story, but one of the key kind of metrics of what the state-of-the-art is how many qubits we have, right? And so the reason I chose these and mentioned them as state-of-the-art is because IonQ offers 79 qubits and Google's bristlecone offers 72. And by the way, notice bristlecone's accompanying quote: "We are cautiously optimistic that quantum supremacy can be achieved with bristlecone." Okay, should be very interesting stuff to see when and if they can really make good on that. And then I've mentioned IBM Q System 1. IBM Q actually has a lot of research prototypes too, and they have a 50 qubit research prototype that they are very proud to announce can hold its state for 90 microseconds, which is a great achievement. Intel has been working on Tango Lake, which has 49 qubits and uses quantum dots. There are a lot of startups in this game too, and one of the notable ones is Rigetti, that has a 19 qubit and is working on a much larger system coming up. And there's a Vancouver company, in case you're not familiar, that's called D-Wave, and they make a machine 2000Q, which has a 2048 qubit quantum annealer. So you think to yourself, wow, 2048, what's with that? Yeah, so I think that it's broadly thought that, that the D-Wave 2000Q is using a quantum phenomenon for a particular kind of problem. And so you should know that in the world of quantum computers, the race is sort of to realize a universal quantum computer that can be programmed for many different problem types. And so it's kind of a thorny set of terrain, but some quantum computers can be used in more specialized ways and will sort of make use of mechanisms and be programmable within a more narrow range of what it's trying to do. And I think the story of D-Wave, as it's broadly discussed, is a bit like that. Okay, so how many qubits do you think we'll have? Or how many qubits do we really need, right? So one thing I want to tell you about the number of qubits is that classical computing can simulate quantum computers up to about something like 60 or 70-ish qubits, okay? So the territory beyond 70 qubits is really where quantum supremacy could be really made, or evidence for quantum supremacy could really show out and establish quantum supremacy. So that's kind of the minimum bar then. And it's very exciting that some of the current prototypes that we see out in the market are sort of pressing on this number now. And that's why they have that number of qubits, because if they can show quantum computing at that point, then it will be a big demonstration of supremacy. Now, there's a whole territory of the number of qubits increasing to the sort of low hundreds. Sometimes they refer to that as the noisy intermediate scale quantum computers. And gradually, I think what you can watch in the press is how the number of qubits sort of gradually goes up and up and up. And as the number of qubits goes into the hundreds or even goes into the thousands, you can imagine how powerful it becomes, since, as I mentioned, the state that can be held is is 2 to the number of qubits that you have. Okay. All right. So another point that I think is very important is that you understand what quantum computers will be able to do. You know, what is the applications? What are the killer apps that they would do? And I often find people asking me questions about, when will I have a quantum computer or quantum processor in my laptop? When will I have one in my cell phone? And well, for one thing, you saw all the cryogenic apparatus, right? So assuming that quantum computers of the future have a lot of cryogenic apparatus, maybe not so likely that you'll have one in your cell phone anytime soon. But I think that the other point is to really think about what quantum computers do well is to work with scientific problems that have an enormous state requirement, right? Beyond things that are even our most performant computers, even the top supercomputers or highly parallel machines, even distributed computing can really do, right? That's what it's going to do well. And of the things I list on this slide, the one I'd really like to point out that there's a great deal of hope about is material science, chemistry, and medicine. There is a great deal of optimism about if and when quantum computing can be realized and scaled to a large number of qubits, that there's a tremendous opportunity to model molecular systems using quantum entanglement. If we could do this, it would go far beyond the kind of simulations that have been done up to this point and could enable us to look at different catalysts, different kinds of pharmaceuticals, different kinds of materials in a way that we haven't been able to do in the past. So I guess I could talk about each one of these in quite a bit of detail. Don't quite have time to do that. But if there's one I might mention that is particularly discussed, I might call that one out as a very popular. Okay. Now, I want to mention that there's another interesting side of quantum computing that you should know about, and that is that it turns out the the researcher, Peter Shor, who's now a professor at MIT, at the time he worked at Bell Labs, discovered a way to apply quantum computers to the problem of integer factorization. I don't know, does that ring a bell, integer factorization? Integer factorization is one of the key underpinnings of our public key cryptography. Do you realize that? Public key cryptography has this thing where you have a mathematical function which allows you to take a private key to calculate a public key, but for the reverse engineering to be very difficult or impossible. They refer to this as a trapdoor function, okay? So it turns out that what Peter Shor is telling you is that if a quantum computer could exist with enough qubits, it could compute a private key from a public key using this algorithm in polynomial time using a quantum computer. Wow, that's really huge stuff. And I don't quite have enough time to tell you how the whole algorithm works, but you can imagine it's something like using superposition to put in the state and then applying some kind of interesting transform that he came up with in order to modify the probabilities that are being held by the entanglement, and then eventually causing the probability of the right answer to sort of emerge as being more probable than all the other possible answers in this. And so voila. It was shown by IBM, among others, that it could be done using sort of a toyish problem. And interestingly enough, not only does this work for integer factorization, but it also can be translated to the discrete logarithm and the elliptic curve discrete logarithm problem, which means that it turns out that quantum computers turn out to be a very big threat to our public key cryptography algorithms that are widely used across the internet right now. So one of the big things I also wanted to tell you about quantum computing today is to be acquainted with this, that at the same time that quantum computing advancement represents a very sort of disruptive computational tool that will be tremendously beneficial in many ways, it's also causing a similar disruption in the world of security as the public key cryptography algorithms that we are using are going to have to be changed to new algorithms. Those new algorithms, by the way, are referred to as post-quantum cryptography. You can think of this name as meaning cryptography that can be used in a post-quantum world, okay? And I don't quite have enough time to go through all of the different sub-branches of it, but there's a number of different camps of these algorithms. None of them are known to be sort of mappable to a quantum computer in any meaningful way. That's why they're thought to be quantum safe. And the National Institute of Standards and Technology is working with the cryptographic community to develop, to sort of select among these possible approaches some standards that we can all use in the industry to replace our cryptography algorithms that are in active use. And so, in addition to choosing the right standards, I just want to mention that the prospect of migrating our whole industry from well-known algorithms that we're using now, like RSA, to these new post-quantum cryptography standards will be a major undertaking. And why? Because quantum computing, because our public key cryptography algorithms are so extensively used throughout the world's communication infrastructure, across our computing stack, whether it's acceleration elements in the platform, whether it's authentication, whether it is identification schemes. They're very extensively used. So to unravel all of our usage of cryptography in order to make these changes using methods in PQC migration and cryptographic agility will really be a serious undertaking for the whole industry. All right, I think I'm out of time, so I just wanted to mention a few resources. Yeah, do take a look at the IBM Q System 1, which has this great information about how their quantum computer actually works. And I think looking at the Caltech pages on the Institute of Quantum Information and Matter is kind of a good way to browse some of the research that's going on in this area that I alluded to about the qubits and different kinds of technology. If you want to take a look at quantum algorithms, yeah, do take a look at the Quantum Algorithms Zoo. That's a really cool website that gives you a whole kind of compendium, and you can browse a few of them in order to see, how a quantum algorithm is expressed and what some of the things are that are out there. The whole issue of post-quantum cryptography, which is a very, very important thing, a very important disruption alongside of quantum computing. I might go take a look at the National Institute of Standards and Technology, which is leading the process of standardizing algorithms, and they have a whole bunch of information about things there. Now, there's one thing that I didn't include in the resources, and I didn't quite have time to talk about, and that is that many of the companies that are working on quantum computer prototypes also have a sort of a software side to what they do, and they've worked on software development kits, and they have environments where you can play with algorithms, play with software with some of their early prototypes. So I encourage you to take a look at some of the companies that I mentioned that have quantum computers and see what they offer by way of software development kits and things that you can play with. The list of companies is a little too long for me to include here, but I think if you do just a little bit of homework, it won't be hard to sort of put your finger on a few of the bigger efforts that they have, including some of the ones that I showed you. All right, I'll leave you with a quote. "Attaining quantum supremacy and exploring its consequences will be among the great challenges facing 21st century science," said by Professor John Preskill at Caltech in the Institute of Quantum Information and Matter. Thank you all very much.